Hello and welcome back. In today's video, we are going to discuss about trees, and it is the sixth video in our data structure series. Trees are a special type of graph where the data is stored hierarchically. As you can see here, the data is stored in different levels. The initial start node or the first node in the tree is called as the root, and the two nodes that are branching out of the root are called as the child nodes for the root. So this is at the first level of the tree. When you come to the second level of the tree, this node becomes the parent, and recursively the two nodes which are branching out of that node becomes the child nodes. So this entire structure becomes another tree called as the subtree. So the property of the trees applies to all the nodes at every level, and each subtree behaves like a tree itself. And all the nodes that are at the end of the tree are called as the leaf nodes. And the distance between the root node and the leaf node is called as the height of the tree. So for this particular tree, if we start with the root node and take a particular path in the tree, say I travel in this path and here, then the height of the tree is 2. So the height of the tree is the distance between the root and the last leaf in the tree. As you can see, tree is nothing but a special type of graph. If you haven't seen the previous video, please go check that out. It talks all about the graphs and various types of graph. So tree is a combination of few types of graph. So it is a connected, all the nodes will always stay connected in a tree, and then it is directed. All the edges that you see in the tree will start from the root and travel all the way across to the leaves, and acyclic. You will not find any cycles within a tree because there will be only one edge connecting a node with another node. So there won't be any edges which are additionally connecting the same nodes forming a cycle. Or there won't be any nodes this way as well. There will be only one edge connecting two nodes. So these are some of the basic properties of the tree. Okay, so I have moved everything to a side so that we can talk about various types of the trees. So the first type of tree that we are going to see today is the binary tree, which is similar to the one which we were seeing so far in the diagram, where every node has at most two children. So this is an example for a binary tree. And the next type that we are going to see is a k-array tree, where each node has up to at most k children. So if you see here, the root node has 3 children, and I could draw 2 nodes for this node, just one node for this, and overall the maximum number of children that a node has is 3. So in this case, this is called as a k-array tree, where k is equal to 3. Binary tree is also a type of k-array tree where k is equal to 2. Since we use this lot more than any other k values, this is given a special name called as a binary tree. And then there are various modulations of the binary tree itself. The first one is a perfect binary tree, where every node will definitely have two children. In the first case where we drew a binary tree, there can be two children for a node, but there can also be just one child or no child for a node. But for a perfect binary tree, there should always be two children for a node up to the leaf nodes. So this is called as the perfect binary tree. And there is another variation which is called as the complete binary tree, which is also called as the almost perfect binary tree. To draw an example for that, so this is called as a complete binary tree where the nodes are filled from left to right. So if in case imagine this node doesn't exist, then this can no longer be called as the complete binary tree. All the nodes should be filled from left to right. This is still a complete binary tree where I drew just a left node but not the right node. However, if I switch this and draw just the right node and not the left node, then this is not a complete binary tree. So a complete binary tree is a tree where the nodes are filled from left to right. So if I remove that right node that we just drew, then this becomes a complete binary tree. And then the next variation is a full binary tree where every node has either two children or no children. So this is a full binary tree, whereas this is not a full binary tree because this node has only one child. So if I draw another child for this node, then this becomes a full binary tree. It doesn't care about the gaps in the tree. So if the left node doesn't have any children, I could still draw nodes for the right node and call this as a full binary tree. So it doesn't care about the gaps within the tree. All it cares about is that each node which has a child should have two children, or it shouldn't have any children at all. So this is called as a full binary tree. So the last tree that we are going to see today is also called as a balanced tree, where the heights of the subtrees are compared. So if you take a look at this tree, this entire structure is called as the left subtree, and in this entire structure is a right subtree. So if we take the heights of the two subtrees and subtract them, if the difference is less than or equal to 1, then the tree is called as the balanced binary tree. So in this case, the height of the left subtree is 2, because if you start from the root node, then you can travel to the last node in the tree by taking 2 steps. And the same applies to the right subtree as well. So the height of the right subtree is 2 as well. And the difference between them is 0. And this type of tree is called as a balanced tree. And if I draw just one additional node in the left subtree, then the height of the left subtree in this case becomes 3 and the height of the right subtree is 2. So the difference is 1 and this is still a balanced subtree because as we said earlier, the height difference can be either 1 or 0 but not more than 1. And if I drew one more node here, then in that case it becomes 4 minus 2, which is 2. So in this case, this is no longer a balanced tree. And we call this type of tree as the left skewed binary tree because the height of the left subtree is greater than that of the right subtree. And if the similar scenario occurs in the right subtree, then it will be called as the right skewed binary tree. These are the basic types of binary trees. There are a lot more types of trees, but these types will appear frequently while solving problems. And similar to graph, the most common operation that you perform on a tree is traversal, where you visit each node at least once, and the time taken for that traversal operation is O of n, where n is the number of nodes in the tree. You will always have access only to the root node, and you will visit every node in the tree recursively. So you will start with the root and you will go all the way to the bottom of the tree, visiting the leftmost leaf node, and then travel one level up and visit the right node, go all the way up and do the same thing with the right subtree. So this is called as a tree traversal and it takes at most O of n time. Okay, before we end this session, I just want to talk about one special type of tree, which is binary search tree. This is something that we will see most frequently in all the problems which involves trees. There will be a dedicated video explaining about the binary search tree in detail along with the programs associated with it. However, I want to give an overview about it because the tree video will not be complete without talking about binary search tree. So a binary search tree is also just another binary tree. However, the way that we store the data within the tree nodes makes it a binary search tree. So let me draw a quick example here. So this is an example for a binary search tree. So notice all the values that are stored in different nodes. First, let's start with the root. So the root node's value is 10 here, and it's okay to store any value as a root node. The constraint starts from its children. All the left children of the root should be lesser than the root itself, and all the right node values should be greater than or equal to the root. So these are the only constraints of the binary search tree. So if you look at the next level, 5 is less than 10, however 15 is greater than 10. And the same property should apply to the next level of the tree. So 2 is less than 5 and obviously less than 10 as well. And 7 is greater than 5, whereas it is less than 10. Because it is positioned to the right of this node, whereas it is positioned to the left of the root node. So it should be lesser than the root node, whereas greater than the immediate parent node. These properties applies throughout the tree. So if you look at the right subtree, 15 is greater than 10 as we discussed earlier. And if you look at the children of 15, the left node will be less than 15, whereas greater than 10, because this side of the tree is to the right of the root, whereas left of the immediate parent. So 12 is greater than 10, however less than 15. Whereas if you look at the right node, that should be both greater than 15 as well as the root node. So the rightmost node in the tree will be the greatest value in the tree, and the leftmost value in the tree will be the least value in the tree. So these are the basic properties of a binary search tree. And the purpose of storing the values in this manner is because it makes the searching process easier. So that hence the name binary search tree. When you're trying to search if a particular value exists in a tree, at each step of the search, you can eliminate the entire subtree. Imagine if I'm searching for the existence of value 2 in this tree, then I'll start with the root node and I'll compare if 10 is equal to 2. No. So I'll check whether 10 is lesser than 2 or greater than 2. So 10 is greater than 2. I immediately know that all the values which are less than 10 will be stored in the left subtree. So I can ignore this entire right subtree and start searching just in the left subtree. And I'll come to the next level and check if 5 is equal to 2. Still no. And since 5 is greater than 2, I know that I can ignore the entire right subtree again and just search the left subtree, which is just 2. And I'll make the final check if 2 is equal to 2, which is what we are looking for, so we can return back to. As you can notice, during the search we didn't traverse the entire tree. Instead, we just went through these 3 nodes. Hence, the time complexity for searching becomes just log n, as we are eliminating the entire half of the tree during each level or each step of the search. This type of eliminating half of the data at each step results in log n time complexity. I have a separate video explaining about the various time complexities where I talk about log n in further more detail. So I'll leave a link of that in the description as well. If you would like, please check that out. Hope I have covered all the basics involving trees. If you have any questions, please leave them in the comments below. These will all become clearer when we start solving problems involving trees. See you soon in the next video. Thank you.